we're recording. Okay, so our introductory lesson for the third unit here is called Composite Functions. And this is a kind of a notation thing. The basic idea of a composite function is probably something that you've seen before. And the notation here is if you see f, and then it looks like a degree symbol. It looks like a little O when you write it, but it's actually like it looks like degrees. F of g of x is how you read this. You literally read this as f of g of x. In other words, put the g of x function into the f of x function. In other words, to kind of show you this as a schematic idea, I give you an x number, you put it in to the g of x function, and then whatever answer comes out of that, you put that into the f of x function. And to go directly from here to here is what we would call f of g of x, or f of g of x. So, for example, this is probably easier to show you how to do than it is to explain what I'm doing. If f of x is x plus 2 and g of x is x squared, find f of g of 3. So what that means is we'll find g of 3, which is plug 3 into the g function, so that would be 3 squared, which is 9, and then find f of 9. So let's see, so what's f of 9? So f of 9 is, that's going to be 9 plus 2, so the answer there is 11. Okay, we'll just pause for the national anthem here, and then we'll keep going. And we're back. And come on, there we go. All right, you're going to notice that I'm leaving lots of room there. That's on purpose. I'm going to come back. I'm going to do all the questions on this sheet one way, and then I'm going to show you how to do them a different way. So leave some room here. And now let's do g of f of x. So again, this is like saying I would like g of f of negative 8, which is saying put negative 8 in the first function, the f function, get a number, put that number into the g function. So the first thing I got to find is what f of negative 8 is. So f of negative 8 is negative 8 plus 2, which is negative 6. And then I want to find g of negative 6. And g of negative 6 is negative 6 squared, which is 36. Okay. Next. That second f should be italicized like the first, but basically what we want is f of 4, or written in the other notation, f of 4. So first of all, we're going to find what f of 4 is. And again, the function for f is x plus 2. So this is 4 plus 2, which is 6. And then I would like to find f of 6, which is again x plus 2, so that's 6 plus 2, which is 8. There are actually lots of functions that you see in math where whatever your output is, you just put it back in the function as your new input. The technical name for that is iteration. You keep iterating a function. Okay. All right, g of f of 3x plus 4. Aha, I'm not just putting a number in, I'm putting in a piece of algebra, in this case a binomial. So again, the other notation for this would be g of f of 3x plus 4. So in the function, so the first thing I'm going to find is I'm going to find f of 3x plus 4. So I'm going to go back to the original function, which is x plus 2. So I replace the x in x plus 2 with 3x plus 4. And that gives me 3x plus 6. Now I'm going to replace the x in g of x with, oh, wait a minute. Did I just reverse the order? Oh, I did. I'm sorry. Can you give me a mulligan on that, guys? I wasn't reading that carefully. Sorry. It wants the g function first. Order matters, and the order that this is happening is it's g of f of 3x plus 4. My bad. I didn't read it carefully. So the first thing I want to do is f of 3x plus... Oh, wait. Is that what I did? It was. The only thing I did wrong was that I thought I was wrong. I could have swore that I misread it, but I didn't. Okay, sorry about that. So f of 3x plus 4 is, what was x again? Oh yeah, x plus 2. So 3x plus 4 plus 2, which is 3x plus 6. I had that right, but I accidentally did write f. I want g here. G of 3x plus 6. So that means I go to the g function, which is again x squared, and I replace the x in x squared with 3x plus 6. And we can expand that. That'd be 9x squared. 3 times 6 is 18. 18 doubled is 36 plus 36. Right? Somebody double check my mental math. 3 times 6 is 18. 18 doubled is 36. Yeah, I think we got that right. Okay, now like I said, there is another way you can approach these. Instead of doing it in 2 steps, you can do it in 1. Remember from grade, I guess it'd be back in grade 10, when you learned, first of all, what function notation means in function. Any 2 variables can have a relation, but it's a function when you define it as a unique relation between every input has its own unique output. Another way to say it is that a function is a rule, right? I take the x number, and what do I do with it? Well, I take the x number, and if it's this rule, I just add 2 to it. If it's that rule, I times it by itself. What if you could put a rule inside of a rule? I sometimes explain functions to my grade 10s with the story, the analogy, that functions are like little machines. A function's like a toaster. You put in a number, you put in a piece of bread, and out comes toast, right? In this case, toasting it is adding 2. Well, this machine here, this is a different machine. This is your microwave. Imagine if you could put your microwave into your toaster. Now, please don't do that at home. Don't try putting your microwave into your toaster, or vice versa. Don't put your toaster into your microwave. Neither of those things will work. But in math, they work just fine. You can put rules inside of other rules. So in other words, why don't I just come up with what f of g of x would look like algebraically? In other words, plug g of x into f of x, and you get that it would be, replace this x with x squared, and it would be x squared plus 2. So if I want now f of g of 3, I just plug a 3 in there, and I get 3 squared plus 2. 9 plus 2 is 11. Let's try the next one that way. What does g of f of x actually look like? G of f of x. So replace the x in g of x with f of x. So instead of x squared, it's x plus 2 squared. And we can expand that. That's x squared plus 4x plus 4. And now let's find g of f of negative 8. Negative 8 squared is 64. 4 times 8 is 32, but it's a negative 8, so that's minus 32 plus 4 is 64 minus 32 is 32 plus 4 is 36. You can even do the same thing with C. Give me a general equation for f of x. What does f of x actually look like? Well, let's see. F of x is x plus 2. So if I replace the x in x plus 2 with itself, it's going to look like that. And that's going to be x plus 4. So is f of 4 going to give me the same answer it did when I did it in 2 steps? Yep. 4 plus 4 is 8. All right, g of f of x. Again, I didn't leave myself much room here. If you got to switch to loose leaf, please do that. Let's get an actual algebra equation for g of f of x. So replace the x in g of x with the function f of x. Okay, we've kind of already done that. It's going to be x plus 2 squared, right? Which is x squared plus 4x plus 4. So now let's find g of f of 3x plus 4. So now we replace these two x's with 3x plus 4. So that's going to be 3x plus 4 squared plus 4 times 3x plus 4 plus 4. And expanding and collecting like terms for that is going to look like this. That's going to be 9x squared plus 3 times 4 is 12, doubled is 24x plus 16 plus 12x plus 16 plus 4. And when I simplify that, I'm going to get 9x squared, 24 and 12 is 36x, 16 and 16 is 32, plus 4 is 36. I got the same answer, which is good because it's the same thing. I just did it in a different kind of order. Now let's just sort of step back and look kind of a general overall of playing with these functions here. Notice that up until the last one, it was actually kind of easier and less steps to find an actual expression for f of g of x or g of f of x, or in this case, f of x, as a piece of algebra and then work with it. Notice that it doesn't matter which way I do it first. So there we go. So there's example 1, playing with functions. Example 2, can we go backwards? If I tell you that I have this function, capital F, and I say that's a composite function, can you break it down into the two functions that make it composite? You would say that, yeah, I would write this as a composite function where f of x is equal to f of g of x. My g of x would be the inside thing, x squared plus 5x, and f of x would be just the square root of x. Get it? So f of g of x would be put the g of x function inside the f of x function, which would look like this. And then, of course, we can just rename that its own function name, which they very often do by saying, oh, this is a composite function, we'll use a capital letter for the function notation. All right, let's try example 2 the same way. If I want to think about this as a composite function, what two pieces is it? What two rules is it? Well, the first rule is I will say that f of x, the first rule is to take the x number, times it by 2 and minus 2. The second rule is take the x number and cube it. So f of x is equal to, what's going to finish that statement? Can you think about it? Am I putting the g into the f, or am I putting the f into the g? You're putting the f into the g this time, right? So it's g of f of x. All right, so there's example 2 for that one. And one more. This one's just purely algebra. Find expressions for f of g of x and g of f of x. Okay, so f of x with a capital is this one. So I am going to put the, I'll write it, first of all, I'll write it in kind of regular notation here, f of g of x. So I'm going to put the g function into the f function. And there we go. And then for the other one, I'm going to do it the other way. G of x with a capital is going to be g of f of x. So we're going to put the first rule into the second rule. So that's going to be the cube root of 1 over 2x. Are these two things the same? No, not necessarily. Okay. In fact, they aren't. Right? For any number I can think of, they would be two different functions. Okay, we have a little bit of room at the bottom, just kind of one thing. And the one thing we kind of have to worry about when we're doing this f of g of x stuff is we have to worry about domain. If f of x has domain restrictions, f of g of x or g of, why don't I write that further over this way, or g of f of x will have the same restrictions, or the same domain restrictions. Like, look at the actual two that we have here. Notice that, for example, f of x here, x can't be 0, right? Because if x were 0, you'd have 1 divided by 0, and you can't divide by 0. Notice in g of x, x could be 0 all you want, right? You can cube root 0. What's the cube root of 0? It's 0, no problem. But because there's a domain restriction here, it still exists there. So that's kind of the basic idea behind that. Okay, one last thing. I'm going to just give you kind of one more thing to kind of look at here. In your fancy new booklets, Applications of Derivatives, we're actually going to start on page 9. So go to page 9. Our first lesson is right here. There we go. I'm just going to run through with you how to do a couple of the questions here, like for example in A, or in number 1. How do you do 1A? I would like to know what g of f of 2 is. So I look at this chart and I go, okay, so f of 2. F of 0 is 0, f of 1 is 2, f of 2 is 4. So, okay, so if f of 2 is 4, I want g of 4. So now I go into the g of x column until I get the input of 4, and the final answer there is 3. Everybody get how I got that? So that's how you do the rest of number 1. Then for a question like number 2, notice that in number 2, f of x and g of x have restrictions on their domain. Like for example, for g of x, there is no value when x is 5. X is 5 just isn't part of the domain for g of x. So even though f of x does have a value at 5, when x is 5, y is 5, f of x is 5. F of g of x does not exist at x equals 5. Or to put it another way, f of g of 5 does not exist. It's like, but it exists fine, it's right here. Yeah, but once the input has run through this rule, can't do that rule. And again, this goes back to my grade 10 analogy. Maybe I could put my toaster into my microwave, but if my toaster can't handle toasting a cheese bagel, because you know the cheese just melts all over your toaster, then you can't put the cheese bagel into the toaster into the microwave. Doesn't work. Even though the microwave can handle your cheese bagel just fine. I might be kind of beating that analogy to death a little bit there. It works great with the grade 10s, let me tell you. Anyway, that's kind of the 2 heads up I wanted to give you. The rest of the examples in this assignment are pretty much exactly the same as the examples that we did in our notes. So that's it. That's today's lesson. I'll stop the video. Thanks for watching it.